Hi there, Miss Barber here. We will begin the idea of the limit lesson. Before we introduce the limit, we will briefly review exercises on how to evaluate and graph functions. After the presentation, work each of these exercises on your own to ensure that you're able to complete them on your own. Exercise. Use the graph below to find the values of x where f of x equals 1 and also find f of negative 2. To find the x values where f of x equals 1, we must first look at the graph where the function itself is equal to 1, and then go to the corresponding values on the x-axis. So we'll notice that reading from the left to the right, the first place this function equals 1 is at x equals negative 6. This occurs again, that is, the function equals 1 at x equals 0. And finally, one last time, the function equals 1, again at x equals 4. Now to evaluate f of negative 2, this means we locate negative 2 on the x-axis and then either move vertically up or vertically down to where the function is. In this case, we move up and we note that at x equals negative 2, the function value corresponds to the 5. Exercise 1.1.2. Sketch the graph of the piecewise defined function and find g of 1. G of x is equal to 2x plus 1 for x equal to or less than 1, and to negative 3x for x strictly greater than 1. This piecewise function has two pieces. In order to graph the entire piecewise defined function, let's graph the first piece first. That is, let's graph, and we'll call it g sub 1 of x, 2x plus 1. Let's observe that y equals 2x plus 1 is a line, and all that is needed to graph a line is 2 points. I will select 1 for x, which is an endpoint on the piecewise definition, and evaluate. 2 times 1 is 2, 2 plus 1 is 3. We have an ordered pair of the line 1, 3. Let's evaluate with x equals negative 2. 2 times negative 2 is negative 4. Negative 4 plus 1 is negative 3. We now have 2 points. Let's plot the ordered pair negative 2, negative 3 on the xy plane, and also the ordered pair 1, 3 on the xy plane. Connect those 2 points, and we observe that we get an increasing line that begins in the third quadrant, intersects the negative y-axis, while it is increasing, intersects the positive x-axis, and continues to increase. We will use a dashed line for the part that's on the right side of x equals 1, as this piece is defined only for x equal to or less than 1. Let's do the same thing for the second piece, which we'll call g sub 2 of x. And that is equal to negative 3x, and we observe again that this is a line. All we need is 2 points to define a line. While x equals 1 for this piece is not defined, we still need to know its location, so let's evaluate at x equals 1, and 1 times negative 3 is negative 3. So we have the ordered pair 1, negative 3. Let's continue, and I will evaluate at x value 2. Negative 3 times 2 is negative 6. So with these 2 points, we'll locate the ordered pair 1, negative 3 and the ordered pair 2, negative 6 and connect. We get a decreasing line that goes through the origin. The graph begins in the second quadrant, cuts through the origin, and continues to decrease indefinitely in the fourth quadrant. Let's observe that the graph drawn has a dashed line for the values to the left of 1 because the piece is defined only for x greater than 1. We will now put the pieces together. So we have the first piece and the second piece. Let's observe that on the first piece, the increasing, there is a solid point at 1, 3, and that's because the piecewise defined said for x equal to or less than 1, and we have an open circle at 1, -3. That's because for the second piece, it was for x strictly greater than 1. So we have this piece, and the question was, what is the function at g of 1? And this means that g of 1 is where we have the solid circle, so g of 1 equals 3. Examining limits informally. Exercise 1.1.3. Consider the function g of x equals x squared minus 3. Complete the table of values for the function g of x as x gets arbitrarily close to or approaches 1. We will accomplish this by using the TI-84. Displayed is a TI-84 CE screen. What we'll do is use the table feature to begin. I will select y equals and then key in the function, which was push the x squared, move over, and then minus 3. Now I want to be able to use the table feature, so I will push the buttons second and window, which gets us to what is called table set. At this point, we don't really care what the table start is, nor do we care what the delta table is, because move down to independent, we're going to select the ask. We get to put in the values and then select enter. Now let's get out of the screen, hit the blue second mode, which lets us quit. Now hit second again and go to table. Now we will key in the values as we approach 1. Since we're approaching 1, let's pick a value less than 1, such as 0, and enter. It evaluates for us -3. That makes sense with the function we put in. Let's approach getting closer and closer to 1, so we'll do 0.99. That's almost 1. And we get -2.02. Let's get even closer, so let's do 0.999, and we get -2.003. Now that's us approaching from the left-hand side, so now let's pick a number to the right of 1. Let's pick a nice whole number like 2. That's 1 unit larger than 1, and the function output is 1. Let's move a little bit closer to the number 1, so we'll go to 1.01, and that gives us -1.98, and let's get even closer to 1, like 1.001. Enter. Now we have -1.998. Let's transfer these values to the table. From the output on the values of the calculator we got for 0, the function is -2. And for 2, the function value was 1. For 0.99, the function value was -2.02. And for the input of 1.01, the function output was -1.98. Remember, we're getting close as possible to 1, but we really don't care what happens at 1. And at 0.999, the function value was -2.002, and at 1.001, the function value was -1.998. If we were making a conjecture, it appears that as x gets closer and closer to 1, again, we don't care what happens at 1, it looks like the function g of x gets closer and closer to what? That's right. Looks like it gets closer and closer to -2. Definition. We define the limit of a function f of x at x equals a as the value L that the function approaches as x gets arbitrarily close to a, but not necessarily equal to a. The notation is the limit as x approaches a of f of x's L is written LIM, and below that x arrow a. To the immediate right of LIM is f of x equals L. Let us observe. 1. Limits do not exist at every x value for all functions. Furthermore, a limit can exist at an x value for which the function does not exist. 2. If the limit L does exist, it is graphically a y value. And finally, 3. The limit depends on the behavior of the function arbitrarily close to an x value, not the function value at the x value. Exercise 1.1.4. Use limit notation to express what was seen on exercise 1.1.3. Exercise 1.1.3 stated, for the function g of x equals x squared minus 3, determine the behavior of the function as x approaches 1. And I've provided for us the completed table of values we earlier obtained. Now let's consider the new notation. The notation format is the limit, and below that is as x approaches a of f of x equals L. Now we need to express the limit of the g of x using this notation. So we would write the limit as x approaches, and the value that it's approaching is 1. Again, we don't care what the function does at 1. We only care what the function does as it gets arbitrarily close to 1 from both sides of the function. And we'll write the limit as x approaches 1 of g of x equals, and we see in the table of values that the function approaches -2. Exercise 1.1.5. Use the graph below to find the limit as x approaches -2 of f of x. Note that there is a hole in the graph when x equals -2. This graph is sinusoidal. That means it's waves that will go up and down the same height or the same amplitude. Now let's observe that for clarity, we know that f at -2 is undefined. It doesn't even exist. So there is no function value there. It's just a hole. However, with the limit, we're not concerned with what happens at that value. We are concerned with what happens near that value. So as x gets closer and closer to -2 from both sides, we observe that the graph of the function approaches -3, even though the function is not defined. So we would express the limit as x approaches -2 of this function f of x is the real number -3. The graph gets closer and closer to -3. Exercise 1.1.6. Find the limit as x approaches 2 of x squared minus 3. To do this, we have several options. One of them is to make a table of values. So let's start with that. Let's remember again that when we're finding the limit, we don't care what the function value is at the x value. We care what the function value approaches as x approaches the limit value. We'll use a calculator again, and I'll just go ahead and transfer the values. I'm going to start with the left side and say 1. That's 1 unit to the left of 2, so that's a good starting point. And in my calculator, I computed -2. Now I put in 3, And so 3 squared is 9. 9 minus 3 looks like 6. Okay, so we are zeroing in from the function value of -6 and function value of -2 and +6. Let's get a little bit closer to 2 from the left-hand side. At 1.9, we get, and wow, this gets close real fast, 0.61. And at 2.1, we get from a function value of 6 at x equals 3 to a function value of 1.41. Let's keep getting closer to 2. At 1.999, the function output is 0.996, and at 2.001, which is almost 2, we get 1.004. So let's observe that as x gets closer and closer to 2, the function, g of x, appears to get closer and closer to 1 from both sides. So using limit notation, write the limit as x arrow 2 right below the lim of g of x equals the limit value of 1. Now we'll consider the graph of g of x equals x squared minus 3. That is an upward facing parabola shifted down 3 units. We can also get the limit if the graph permits. So we want to know what happens as x gets closer and closer to 2. And when we do, we observe that the function gets closer and closer to 1. So we get that value by looking at the graph as well. And let's continue to practice using limit notation. So we see that the limit as x arrow 2, read limit as x approaches 2, of the function g of x approaches the limit, which is the real number 1. Exercise 1.1.7. Consider the tables below. Discuss the behavior of each of the functions as x approaches the value specified. Express the answer using limit notation. A. As x approaches -2, the table consists of 2 columns followed by 1, 2, 3, 4, 5, 6, 7 rows. The first row labels the columns, with the first column being x, so we are looking at input values of, we'll start with -2.1, and evaluated in the function that gives you -0.05. Now I'm going to go ahead and look at -1.9 evaluated in the function. It appears identical to what the value was at x equals -2.1, and that is the function output is -0.05. We might be able to observe that without the equation and without the graph, the table suggests that it is symmetric about the value of x equals -2. And at x equals -2.1, the function value is -0.0005, and at x equals -1.99, it has the same function value, -2.01. The function value is -0.0005. And let's observe that very immediate left and very immediate right of -2, so -2.001 and -1.9999 both approach -0. A whole bunch of zeros followed by 5. This suggests that the function actually is approaching 0, so we would write that the limit as x approaches -2 means gets closer and closer and closer and closer to -2. The function appears to approach the real number value of 0. Now let's look at b. As x approaches 4. Let's begin at the left of 4. And so at the left of 4, the table starts at negative 3.9. It gives us negative 174.05 for the function. At positive 3.99 for x, the function output is negative 179.4005, and at x equals 3.9999, the function value is negative 179.994. So as we approach 4 from the left, and let's go ahead and write the words. As we approach 4 from the left, the function f of x appears to approach negative 180. Now let's look at what happens as we approach 4 from the right. And that is at 4.1, we got 186.05 for the function output. At x equals 4.01, the function value is positive 180.6005. And finally, when we get to x equals 4.001, the function value of f of x is positive 180.006. So we say as we approach for the x value from the right, f of x approaches positive 180. They don't meet. So at this point, we say that the limit does not exist. Definitions of the left-hand and right-hand limit. The notation, limit as x approaches a of f of x equals L, means the limit is approached from x values both less than and greater than a. To consider the limit from only the values to the left of a or from only the values to the right of a, we use one-sided limits. They are left-hand limits. The limit as x approaches a from the left of f of x equals L, where x is less than a. The notation a superscript minus is read left of. Right-hand limits. The limit as x approaches a from the right of f of x equals L, where x is greater than a. The notation a superscript plus is read right of a. Exercise 1.1.8. Find the left-hand and right-hand limit for the function represented by the following table of values. This table of values is copied from the previous exercise. Find the limit as x approaches 4 from the left of f of x. From the left means less than, so we are looking at the function behavior provided by the corresponding values for the x input of 3.9, 3.99, and 3.9999, and it appears that this function approaches negative 180. Now find the limit as x approaches 4 from the right, which means we're going to go from values larger than 4, such as 4.1, and decrease progressively until we get very close to 4. And in this table, we see that the limit as x approaches 4 from the right of f of x is 180. Existence of a limit. If the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x equals the same real number value L, then we say that the limit exists and the limit as x approaches a of f of x equals L. If the limit as x approaches a from the left of f of x does not equal the limit as x approaches a from the right of f of x, then we say that the limit does not exist. Note, if either the left or the right-hand limit does not exist, we also say that that limit does not exist either. So now, for the function we've been working with in the table of values, find the limit as x approaches 4. Let's observe that in the previous exercise, we found that the limit as x approaches 4 from the left of f of x is not the same as the limit as x approaches 4 from the right for f of x. Since the limit values are not the same from the left and the right, we say that the limit as x approaches 4 of f of x does not exist. Exercise 1.1.9. Find the limit as x approaches 1 from the left of the quotient absolute value of x minus 1, all divided by the quantity x minus 1, and the limit as x approaches 1 from the right of the quotient the absolute value of x minus 1, all divided by the quantity x minus 1. For the solution, I made a table of values to help determine the left-hand and right-hand limits. So let's look at the table of values where I selected for the first column x and for the second column f of x. When 0 is keyed in, okay, that would be from the left of 1. We would put in 0 for the x's and we get the absolute value of negative 1 divided by negative 1. The absolute value of negative 1 is positive 1, and 1 divided by negative 1 is negative 1. This will work for 0.9 also. That is, the absolute value of 0.9 minus 1 would give a positive value, and 0.9 minus 1 would be a negative value of the same scalar value, and so that limit will also be negative 1. Now let's look at an x value of 2. The absolute value of 2 minus 1, or just 2 minus 1 is 1, and in the denominator 2 minus 1 is also 1. The absolute value still maintains the same, so 1 over 1 is 1. And this works similarly for all values less than 2, but greater than 1, that is to the right of 1. So from the table, we gather that the limit as x approaches 1 from the left of the function is negative 1, and the limit as x approaches 1 from the right of the specified function is positive 1. Let's observe that the limit does not exist since the left-hand and right-hand limits are different. We'll continue with the previous exercise. Let's look at the graph of that function, y equals the absolute value of x minus 1, all divided by the quantity x minus 1. The graph shows two horizontal rays. To the right of 1, we have a horizontal ray, or a line with one starting point at x, starting at x equals 1. It extends to the right. Notice that the starting point is an open hole because at x equals 1, this rational function is undefined. Similarly, for x less than 1, we have the graph of a horizontal line or ray at y equals negative 1, and at the x value of 1, we have an open hole. This graph matches the values that we got by completing the table of values. Use the graph of f of x below to answer the questions that follow. The graph is a piecewise function with two pieces. The first piece, reading from the left to the right, is a decreasing line. It begins in the second quadrant, intersects the positive y-axis at 5, continues to decrease until it comes to an open hole at the ordered pair value of 3, 2. The second piece is a downward-facing parabola, 1/2 that is right side of the graph. It has a closed hole beginning at the ordered pair 3, 5, and then it decreases, intersecting the x-axis to the right of 5. A. Find f of 3. That's the function value at x equals 3. When we look at the graph, we observe that there is a solid circle where the x value of 3 corresponds to, and that's for the parabola at 5. The function value at x equals 3 is 5. B. Find the limit as x approaches 3 from the left. That means we ignore what happens to any part of the graph to the right, and as x approaches 3 from the left, it follows along the line, and the limit approaches 2. Now find the limit as x approaches 3 from the right of f of x. As we approach 3 from the right, we ignore any part of the graph to the left of 3. As the x gets closer and closer to 3, the function value reaches the top part of the parabola, which is the solid hole at the value of 5. And now part D, find the limit as x approaches 3 of f of x. In parts B and C, we computed that the left-hand and right-hand limits as x approaches 3 is not the same, so we conclude that the limit as x approaches 3, we'll write D and E for does not exist. Continuing, find the function value of 4. So f of 4, we move either up or down from the x value until we hit a graph, and the portion of the graph we hit is the parabola, and the corresponding y value is 4. Now let's consider the function, the limit as x approaches 4 from the left of 4. So we get closer and closer and closer to 4 on the x-axis, and we see that the function also approaches 4. Now find the limit as x approaches 4 from the right. So if we approach 4 from the right on the x-axis and follow along on the graph, the function also approaches 4. And H, the limit as x approaches 4 of f of 4. We glean from parts F and G that the left-hand and right-hand limits are 4. They are the same value. Therefore, the limit by itself with no left or right is also 4.